Now, for stars like our Sun, the collapse continues until it produces a new and exotic type of star. The vast expanse of space, where time and reality intertwine, has always posed one perplexing question to humanity: what happened before the Big Bang? For generations, the Big Bang theory stood as the cornerstone of our understanding of the universe's birth. But what if that was only the beginning of the story? What if there was a time before time, a reality before the explosion that birthed our cosmos? Stay tuned as Brian Cox reveals something significant in theoretical physics, peers into the abyss of quantum speculation, and grapples with concepts that defy conventional wisdom. Contemporary scientific understanding elucidates the genesis of the universe through the framework of the Big Bang theory. According to this theory, our cosmos originated from the explosive release of energy from a point in spacetime known as the Singularity, where energy density and mass approached infinity while all dimensions converged to zero. However, recent statements by Brian challenge this theory, asserting that the universe has perpetually existed, rendering the Big Bang theory erroneous. The Big Bang theory postulates the existence of a singularity devoid of time, space, or matter. This raises critical questions about the origin of the singularity, what preceded it, and the mechanisms that triggered the commencement of the Big Bang. It beckons the query of whether the universe has an eternal existence or if it has a definitive beginning. For scientists, particularly physicists and biologists engrossed in the fundamental essence of life, the quest for understanding takes them to the very genesis. A depiction of the origin and progression of the universe as it stands has been drawn. A recent, meticulously precise measurement of the universe's age places it at approximately 13.75 billion years old. Nevertheless, the why behind the universe's inception remains an enigma. Questions about events preceding the Big Bang persist, highlighting the ongoing research in this domain. Based on current understanding, what is certain is that the universe was incredibly hot, dense, and minuscule 13.75 billion years ago. Astonishingly, everything we presently observe in the universe was at some point compressed into a space possibly smaller than an atom. The universe has since expanded and cooled, giving rise to complex structures, including DNA, celestial bodies, and life as we know it. Efforts to unravel these mysteries involve stargazing and the construction of instruments capable of replicating the conditions near the Big Bang. These endeavors seek to discern the origin of the universe and the mechanisms underlying its development. Centuries ago, St. Augustine pondered the nature of God's existence before the universe's creation, concluding that time was a creation of God and there was no before. In the 20th century, Einstein's theory of relativity linked mass and time, demonstrating that time flows differently in proximity to massive objects. Consequently, the concept of time and causality became intertwined. Einstein's viewpoint suggested that discussing events before the Big Bang was futile, as there was no before. Nonetheless, this notion challenges the fundamental principles of causality in physics, where every effect has a cause. Einstein's assertion that nothing existed before the cosmic singularity appears counterintuitive, as it implies the absence of a past. This raises questions about the validity of such a proposition. Despite ongoing debates, the scientific community maintains strong confidence in the Big Bang theory. According to this theory, the universe isn't expanding into something, rather, space-time itself is expanding. Space and time are thought to have originated with the Big Bang and have been stretching since. Einstein's theory of general relativity, developed in 1915, forms the bedrock of these concepts, supported by real-world evidence like American astronomer Hubble's 1929 observation of the universe's expansion and the American scientists Penzias and Wilson's 1965 discovery of cosmic microwave background radiation. This radiation, appearing 379,000 years post-Big Bang during hydrogen recombination, aligns with the theory. The Big Bang theory proposes that within the first second of its birth, the universe was as tiny as an atom but has gone through 6 stages. According to Brian, these stages, including the Planck, grand unification, inflationary, electroweak, quark, and present-day phases, have significantly influenced the universe's structure and fundamental forces. The hadron phase, marking a crucial moment when the universe shrank to the size of an atom 1 second post-Big Bang, is noteworthy. At this scale, quantum theory governs classical physics. Esteemed cosmologists such as Stephen Hawking pondered whether quantum theory, which effectively explains subatomic phenomena, could be extended to encompass the entire universe. This led to the birth of inflationary quantum cosmology, hailed by prominent astrophysicist John Gribben as the most profound scientific advancement since Isaac Newton's era. In essence, inflationary quantum cosmology provides a framework to address the mystery of the cosmic singularity, challenging the classical belief that it was a point with zero volume. However, quantum theory introduces an inherent element of uncertainty at the most basic level of nature, making it impossible to pinpoint the exact moment of the universe's inception or its initial volume. An intriguing facet of quantum theory is its allowance for the spontaneous emergence of particles from the vacuum. Quantum cosmologists pondered whether the universe itself could have arisen from a random fluctuation adhering to the principles of quantum mechanics. If this were the case, the very reason for the existence of something lies in the inherent instability of the vacuum. In the realm of physics, a vacuum refers to a state devoid of particles, yet it is not entirely devoid of properties. Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics, dictates that certain pairs of properties cannot be accurately measured simultaneously. For instance, the more precisely we know the position of a particle, the less precisely we can measure its momentum and vice versa. Another such pair is time and energy. Greater precision in measuring the time of an event results in less precision in measuring the energy associated with that event. This brings us to the notion that a perfect vacuum, where all field values remain constantly at zero, is in direct contradiction to the Heisenberg uncertainty principle. According to this principle, if the value of a field is known with absolute precision, its rate of change becomes entirely random, preventing it from remaining zero at all times. In simpler terms, pure emptiness is inherently unstable, and true emptiness as we might imagine it does not exist. According to Brian, the concept becomes even more astonishing when we consider that a universe comprising billions of galaxies could have emerged from what we typically perceive as nothingness. All mass, as famously described by Einstein's equation, represents a condensed form of energy. However, this vast positive energy bound within stars and galaxies must be counterbalanced by an equal amount of negative energy stemming from their gravitational pull. In a closed universe with a finite lifespan destined to eventually contract, these positive and negative energies must harmoniously balance each other, resulting in the total energy of such a universe being precisely zero. Stephen Hawking delved into the intriguing question of how the universe might have originated from nothing. He pondered the possibility of creating a celestial body without an increase in its overall energy, given that forming any physical entity requires an expenditure of energy. This line of thinking led to the significance of gravity, which possesses negative energy due to its attractive properties. To separate objects gravitationally bound, such as the Earth and the Moon, energy must be expended. This negative energy could potentially be balanced by the positive energy needed for the creation of matter. However, the scenario becomes more intricate when considering celestial bodies like stars. As a star diminishes in size, its negative gravitational energy intensifies, ultimately surpassing the positive energy inherent in matter. This critical point results in a star collapsing or condensing into a black hole. Paradoxically, a black hole contains positive energy while empty space remains stable. This implies that objects like stars or black holes cannot spontaneously emerge, nevertheless, the entire universe can. Quantum mechanics aligns with Stephen Hawking's conclusions. American scientist Alexander Vilenkin demonstrated that a minuscule vacuum filled with energy can spontaneously emerge from a state of emptiness due to negative pressure from cosmic inflation. This energized vacuum rapidly expands, reaching cosmic dimensions within microseconds, emitting light and matter, ultimately culminating in the Big Bang. Consequently, a compelling explanation emerges: the universe originated from nothing. Before this event, there was neither energy, nor space, nor time. The duration of this nothingness is irrelevant since time did not exist. During this era of nothingness, our universe arose from a random quantum fluctuation of the void. However, it raises the question of whether this quantum fluctuation was genuinely random, echoing Einstein's assertion that God doesn't play dice. This revelation prompts contemplation of its implications and the possibility of another energetic vacuum spontaneously reappearing, triggering a new Big Bang, potentially posing a 100% probability of humanity's obliteration. In the realm of physics, certain fundamental constants underpin all physical laws. These constants include the speed of light, the gravitational constant, Planck's constant, the masses of the electron and proton, and the charge of the electron. Deviations, even slight ones, in any of these constants could have profound effects on the universe. These constants would render our universe non-viable. For instance, altering the speed of light would disrupt the stability of atoms and stars. The precise tuning of these constants remains a perplexing enigma. Additionally, the question arises as to why our universe is three-dimensional even though Minkowski's space encompasses four dimensions in the geometric interpretation of the special theory of relativity. Imagine that we reside not in a three-dimensional space but on a two-dimensional sheet. In this scenario, forces such as light and the strong nuclear force operate solely on this sheet. What if there were another universe, another sheet floating just a fraction of a millimeter away? We wouldn't perceive it because light and forces are confined to our sheet. This intriguing concept challenges our understanding of the cosmos. We now contemplate the validity of this proposition, which prompts us to conduct experiments to discern its presence. It's worth noting that while not widely acknowledged, certain telltale signs of these additional dimensions have been postulated. These enigmatic dimensions have been hypothesized to manifest within the Large Hadron Collider at CERN, albeit within a highly speculative context. It's remarkable to consider the possibility of an alternate universe existing in such close proximity, a mere millimeter away, extending infinitely in all directions yet invisible to us due to the governing forces that keep us bound to our own plane. Paul Ehrenfest's revelation adds a fascinating layer to our understanding, suggesting that in realms featuring four or more spatial dimensions, the stability of planetary orbits becomes untenable, rendering the existence of our universe implausible. In light of these observations, scientists have introduced the concept of the Anthropic Principle. This principle posits that observers not only have the potential to influence the universe but can also impact the laws governing it. There are two iterations of this principle, the weak and the strong. The weak anthropic principle asserts that our universe exhibits a structure conducive to the emergence and evolution of life. In contrast, the strong anthropic principle posits that the universe inherently possesses properties that allow for the evolution of intelligent life. A nuanced variation, the participatory anthropic principle, suggests that phenomena only attain existence upon observation, implying that observers may play an integral role in conferring meaning to our universe. However, it's essential to acknowledge that alternative hypotheses exist within the scientific community. One such theory, the concept of cosmological natural selection or second universes, is a topic of ongoing discourse. This theory postulates that each black hole within our universe begets a new universe on its opposing side. Within these alternate universes, fundamental physical constants may deviate from those in our universe. The emergence of intelligent life is contingent upon these varying constants, resembling the process of mutation and selection observed in biological evolution. For some scientists, this model offers a more plausible explanation for the fine-tuning of our universe. In the theory of second universes, life emerges through a natural selection process, wherein universes possessing favorable parameters for the formation of more black holes would have a greater number of descendants, subsequently enhancing the likelihood of life's presence. In a recent episode of the BBC series, Universe, where everything begins and ends, Brian delved into the fundamental question of the universe's origin. Brian explained the Big Bang theory and introduced a captivating perspective by suggesting the existence of a dimension of time before the Big Bang. This intriguing idea expands our understanding of the universe's birth and aligns with the theory of cosmic inflation. According to this theory, the universe rapidly expanded shortly after the initial Big Bang, resulting in its remarkable smoothness and uniformity across large scales. While inflation is a key part of the prevailing cosmological model, Brian's concept of a pre-Big Bang state adds complexity to the universe's evolutionary history. This leads to the question, what triggered this early expansion? Could it be due to interactions among incompletely understood forces? Brian's ideas about the time before the Big Bang are supported by the research of Sir Roger Penrose, a distinguished mathematician and physicist awarded the Nobel Prize in Physics for his groundbreaking work on black holes. Penrose's research extends beyond black holes to explain the early universe. He introduces the concept of eons, representing cosmic epochs occurring in a cyclical pattern. Each eon begins with a Big Bang, followed by expansion, contraction, and ending in a big crunch where the universe returns to its original state. This cyclic process continues indefinitely. At the heart of Penrose's eon theory lie black holes, cosmic entities born from the gravitational collapse of massive stars. These extraordinary objects gradually diminish over immense time spans, emitting energy through Hawking radiation until they ultimately vanish. Penrose suggests that remnants of these dormant black holes from previous cosmic epochs may persist into our current era, possibly leaving discernible imprints on our observable universe. These remnants, which Penrose dubs Hawking points in tribute to the late physicist Stephen Hawking, appear as slightly warmer regions in the sky roughly 8 times the diameter of the Moon, detectable through advanced observational techniques. While the concept of Hawking points awaits further empirical confirmation, its central role in scientific discussions highlights the evolving nature of our understanding of the universe's origins. The discourse surrounding these enigmatic points emphasizes the need for ongoing scientific exploration and the potential for revolutionary insights in the future. Yet, as is customary in pioneering scientific proposals, both Brian's and Roger Penrose's theories about a temporal era preceding the Big Bang face challenges and controversies. Critics argue that the idea of a pre-Big Bang universe remains speculative due to the absence of direct observational evidence. Additionally, Penrose's cyclic eon theory raises questions about energy conservation and the ultimate fate of the universe, prompting skeptics to doubt the feasibility of an infinite cycle of cosmic epochs, which may appear to contradict well-established laws of thermodynamics and other fundamental principles of physics. Now, let's explore another important idea in cosmology, the multiverse hypothesis. This concept suggests that there are many universes, each with its own set of physical laws, constants, and properties. The idea behind this is that our universe might be just one of many in a vast and diverse multiverse. The multiverse concept has gained popularity as a way to explain certain aspects of our universe that seem to be finely tuned to support life. Scientists have noticed that the fundamental constants and physical laws in our universe appear to be carefully balanced to allow life as we know it to exist. Some have proposed the Anthropic Principle, which suggests that our universe has specific characteristics to accommodate intelligent beings like us. However, this idea of a finely tuned universe raises the question of whether it's just a lucky coincidence or if there's a deeper explanation. The multiverse hypothesis suggests that there are countless universes, each with different physical properties. In this vast array of universes, finely tuned ones would naturally arise, and we happen to be in one of them because life as we know it wouldn't be possible in any other type of universe. One version of the multiverse theory is the inflationary multiverse. According to this idea, shortly after the Big Bang, the universe went through a rapid expansion called cosmic inflation. During this expansion, different regions of space could have expanded at different rates, creating separate bubble universes. Each of these bubble universes would have its own unique physical laws and constants. While the multiverse hypothesis is intellectually stimulating and provides an answer to the question of fine-tuning, it faces significant challenges. One major challenge is the lack of direct evidence for these hypothesized universes beyond our own. Since these proposed universes are not connected to ours in a causal way, testing or observing them directly is an extremely difficult task. Critics of the multiverse theory contend that it lacks empirical verification and resides in the realm of untestable speculation, positioning it more as a philosophical notion rather than a scientific theory. They argue that the multiverse's explanatory potential is limited since it fails to offer verifiable predictions that can be substantiated through observations or experiments. Nonetheless, despite these challenges, some physicists and cosmologists find the multiverse hypothesis compelling due to its capacity to address specific cosmological puzzles. For instance, it can potentially elucidate the concept of eternal inflation, where new universes continually emerge through inflationary processes, possibly explaining the vastness of our cosmos. Others view the multiverse as a framework for comprehending the fundamental nature of reality and the existence of multiple potential outcomes within the quantum realm. In quantum mechanics, particles can exist in multiple states simultaneously until observed, raising the inquiry of whether all conceivable outcomes exist concurrently in parallel universes. The multiverse hypothesis also intersects with string theory, a theoretical construct in physics postulating the existence of higher dimensions beyond the familiar four dimensions of spacetime. Some variations of string theory propose a landscape of possible vacuum states, each corresponding to a distinct universe with unique physical properties. While the multiverse remains the subject of ongoing debate and investigation, it serves as an indispensable thought experiment in cosmology. It pushes the boundaries of our comprehension of the universe and encourages scientists to explore ways to delve further into the limits of our knowledge. Thanks for watching another episode of Voyager. While you are still here, make sure to click the video on your screen for more quality content.